So, welcome back to the lecture series of finite volume, and where we will continue our discussion where we left in the last lecture. So, if we put the collocated algorithm together, so collocated simple algorithm. So, what it says that, so again you start with guess values which is Pn Un m dot n, then solve the momentum equation to get V star, then update the m dot using Riccio interpolation and compute the momentum satisfying mass field. Fourth, now you solve the pressure correction equation to get P prime. Now, with the pressure correction field, so now you update velocity and pressure field, U and pressure field, and also the mass flow rate which is U double star, P star, m dot double star, and check. So, now you can treat this new solution to be the updated solution to be the new guess if it is mass conserving. So, treat the obtained solution to be new guess. If it satisfies everything, stop here, otherwise you can go back to step here and repeat it. Once you get a converse solution, then move to next time level integration. So, in every time level you carry out this process to get a converse solution, and then you keep doing this. So, if someone put the flow chart which will look quite nice, it is let us say set initial guess which is m dot n, V n, rho n, P n at time t plus delta t to converged value at time t. Then from there you assemble and solve momentum equation to get V star. From there one can compute m dot f using Riccio interpolation, m dot f star, then assemble and solve for P prime pressure correction. From there you can correct m dot star f, V star, rho n and P n to get m dot star star f, V star star f, rho star star and P star star. Now you can set m dot n f equals to m dot star star f dot v n equals to v star star, rho n equals to rho star and p n equals to p star. So, converged, if no, then from here you go back to this process and repeat. So, if this is no, if it is not converged, then go back and repeat this process. Now, if it is yes, then set solution at t plus delta t to be equal to the converged solution. Now, you advance in time and set t equals to t plus delta t. Now, if time exceeded, yes to stop, it will get you stop. If no, from here you go back and repeat. So, this is no. So, this goes in physical iteration, and within that this is a iterative process, and this is how you get solution for the simple algorithm get working. So, for this collocated arrangement. Now, moving ahead, once you get a system ready, then it is important to also see how one can implement the boundary condition. So, to do that, let us start working on the boundary condition, and this is an example of boundary element. So, this is an example of a boundary element where you can see this is the boundary face and this is the cell center and this is the direction of that and this is the surface vector. Now, one important thing is that when the face located at a boundary patch, this is the boundary face has to provide the boundary condition. Now, the first thing to be of interest is the expression of the Ree-Chow interpolation at the boundary face. So, which now the Ree-Chow interpolation at boundary face needs to be modified. It needs to be modified at boundary. So, what one can write that any variable which is at boundary is variable of the C. So, B refers to the boundary face, and in that way the adopting this practice average the Ree-Chow interpolation. So, at the boundary values can be written as V C star delta P B at n equals to delta P C at n and d B V equals to d C V. So, this one can do, and your B B star equals to V B star bar minus d C V delta P B n minus delta P B n bar, and this is your standard Ree-Chow interpolation, which one can write minus d C V delta P B n minus delta P V P B C n bar. which is at the boundary face Riccio interpolation, and the mass flux which can be written as m dot b equals to rho b v b star dot s b, which is rho b v c star minus d c v delta p b n minus delta p c n and dot s b. So, if you expand this would be v star dot s b minus rho b d c multiplied by p b n minus p c n minus rho b d c v del p b n dot t b minus. So, this is a component which comes along this line and the tangential or the deferred corrections along the normal line. So, that has this component. So, this is a implementation of the boundary condition which presented for the momentum equation. Now, secondly, we can look at the boundary condition implementation for the pressure equation or the pressure correction equation, and for the cases when the boundary condition for the momentum and pressure corrections equation are codependent, then you need the full treatment of the pressure correction equation. Now, momentum equations, once we look at it, so for momentum equation, the semi discretized form looks like rho v c minus rho v c divided by delta t v c, which is previous time step. So, plus summation of f n b c m dot f v f. So, this is elemental discretization phase integration equals to summation of n b c p f s f. This is again phase discretization plus summation of tau f dot s f. This is also phase plus b, which is again elemental discretization. Now, these are already taken care of individually. So, straight away what we can write for this phase, which is m dot f v f, one can write that interior n b m dot f v f plus m dot b v b, which is at boundary phase, and these are all interior phase. So, you can decompose into two component, and similarly one can decompose the component of the stress component tensor, which is again f at the interior n b c tau f dot s f plus tau b dot s b. So, this is at boundary phase, which one can write summation of f interior n b c tau f dot s f plus as a source term. And similarly, the pressure discretization of the boundary phase, one can write f interior phases p f s f plus PBSB. So, this is at boundary phase. So, one has to look at individual component and then treat the boundary values. So, for example, now if you come to wall boundary condition, now this is wall boundary condition. What you have no slip wall. So, you can see this is my face or the boundary face, and the no slip wall condition means what you do not know Pb, but you know mass flux is 0 and you know the velocity of the boundary face is wall. So, this is the boundary face. Now, no slip boundary condition means you have a velocity, but typically this would be 0. So, now what one can do, this the Fb that can be expanded as A plus A parallel component. So, the Fb can be extended on the fluid can be written as this, where this guy represents the tangential direction to the wall, tangential direction to wall, and this is the normal direction. So, which means this would be along this direction normal and this is along the tangential direction. So, the Fb would be F this. So, in the normal direction, which is supposed to be actually 0. So, the parallel direction would be tau wall Sb. Now, tau wall is the shear state wall which can be calculated as del V tangential to the directions by del D perpendicular direction. So, V is the velocity vector parallel to the wall. So, this is a parallel to the wall, and D perpendicular is the normal distance. So, this is how, so this is the parallel to wall and this is the normal distance. So, unit vector would be Sb by Sb, where Nx, Ny, Nz would be the component, then D perpendicular would be dCb dot n, which is dCb dot Sb by Sb, and V parallel would be V minus V dot n n, which will let you have U minus U nx plus V ny plus W nz and nx, V minus U nx V ny W nz ny and W minus U nx V ny W nz nz. So, this is how you compute all these component and you can calculate the tau wall, which would be minus mu b Vc minus Vb, which is parallel, D perpendicular, minus mu b, which can be written as Vc minus Vb minus some Vc minus Vb dot n n, and this is D perpendicular, and you get all these component like Uc minus Ub minus Uc minus Ub nx, Vc minus Vb ny plus Wc minus Wb nz multiplied with nx. So, this term would be common. So, one can write similarly Vc minus Vb minus, this is the same term multiplied with ny, and WC minus WB minus same term multiplied with NZ. So, that is what one get. Now, for laminar flow, now this is what one can obtain. Now, another the thing is that u component direction, the coefficients of the boundary elements for the momentum equation. For u component, in that direction your ACU would be written as ACU plus mu b SB by d perpendicular 1 minus nx square. So, this is the contribution due to boundary phase, and this is interior phase. Similarly, AFU equals to B0 and BCU would be BCU plus mu b by d perpendicular SB UB 1 minus nx square plus VC minus VB NY nx minus WC minus WB in Z nx minus PB SBX. So, this is the contribution come from the boundary and this is from the interior phase. Similarly, one can actually get the V component and W component. So, it can be obtained similarly, all the matrices are already been written. Now, the important point which comes is that at the boundary the pressure Pb which is unknown and it needs to be extrapolated from the interior solution. So, one can use some sort of a Taylor series expansion and write that Pb equals to Pc plus delta Pc dot dCb. Now, the mass flow rate which is expressed as a rho chow interpolation which will have the contribution like this delta Pb n minus delta Pcn dot Sb. Now, the mass flow rate and the velocity at wall boundary, at wall the mass flow rate is 0, velocity is also 0, then this guy boils down to 0 equals to 0 minus rho b dCb minus delta Pbn minus delta Pcn dot Sb. So, which one can modify it and like write that n dot Sb equals to delta Pbn dot like this, which is delta Pcn dot Sb. Now, Sb has two component like Eb plus Tb. So, one can write this term delta Pbn dot Eb plus Tb, which will get you that delta Pcn Sb prime. So, one can write dC Pb minus Pc equals to delta Pcn dot Sb prime minus delta Pb n dot Tb. So, all this when you put together you get Pb equals to Pc plus delta Pc at previous time iteration dot minus Pbn dot Tb by dC. Now, similarly, one can have slip wall. So, this is an example of slip wall, and at slip wall what happens, your Pb is still unknown, mass flow rate is 0, force is 0. So, what one can modify that, coefficients would be like this AC. So, this is only contribution come from interior faces, and AF equals to B, which 0, and BC is V minus B, which is again interior faces and boundary faces. So, one can see, once you write everything mathematically in this fashion, then when you come to a particular application of the boundary condition, then it becomes quite easier. Now, this is a case where you have a specified velocity. So, when you have a known velocity, which means Pb is still unknown, m dot b can be specified, and Vb is specified. So, one that is the case, then you can have this calculation like Pb equals to Pc plus delta Pcn dot dCb, and your other things will get modified. ACV is ACV and BCV, which will modified like AF equals to BVB, and AF equals to BV is 0, and the convection mass flow rate m dot Vb and diffusion time at the boundary face can be calculated. So, like this AB equals to tau B dot SB and m dot B Vb, this can be calculated as the given condition is known. Now, similarly, one can have specified pressure. So, this case is a specified P. So, the pressure specified at the boundary, which means my Pb is specified and m dot b is not known. So, velocity b is also not known. So, one has to modify the equation of the mass flow rate. Correction mass flow rate would be rho b Vb correction dot Sb, which will be rho b Vb star star Eb dot Sb, which get you back the Vb star star equals to m dot b star star divided by rho b Eb dot Sb, which is Vb star star and Ev. So, we can actually see the other kind of boundary conditions also in the next lecture. So, we will stop here and take it up from here in the next lecture. Thank you.